Okay, so let's start with any of you. So Sion, what is the problem you're having primarily with the scanning MLP?
Professor, can you hear me?
Yeah. Yes.
So yeah, I think I'm still like having some difficulty like understanding like how to like convert a scanning MLP into a CNN, because I think I understand like how do we convert a CNN back to a scanning MLP, but from the other way around, I'm not sure how can I do that as
Okay.
in the
So let's start with the problem, right? Which problem are you speaking of in particular?
the part one problem.
So I'm trying to. I don't have decline. Part one. Let me. This is number one, number two, part one. Right up. So I have a problem over here. Which one are you speaking of particularly? Part one, there are several parts, right?
Right. So it's let me see. It's 5.1. It's actually the entire like problem number 5.
Okay. So CNN scanning MLP, is that the one that you want, or
yes,
5.1?
Yes.
Okay. So let's. Can you see my screen? Okay. You're given a. Yeah. Okay. You're given
I can see your blackboard. Yes.
Yeah. Okay. So you're given a 128. Let me erase this. So that you're given a 128 cross 24 input, right? So instead of drawing it like this, just for convenience sake, let me draw this with bars. So each of these bars is 24 components, and you have 128 of these. Okay. The MLP evaluates 8 contiguous input vectors at a time, right?
Yeah.
So it's looking at 1, 2, 3, 4, 3, 4, 5, 6, 7, 8. 8 of these at a time. So it's effectively scanning for 8 time instant wide patterns. It strides forward 4 time instants. So which means that after scanning this segment, right, the next segment it's going to scan is this one. Correct?
Yes.
Does that make sense? So the next time it's going to be looking at this. Okay. Okay, fine. Then the MLP itself has 3 layers. It has 8 neurons in the first layer, 16 in the second layer, and 4 in the third. Right? Now, so it's I'm going to use the vertical, it has, wait, 3 layers, 8 in the first layer. So it has 8 neurons over here, 16 neurons over here, and what is how many in the third one? 4 in the third, right? 4 in the third. Okay. For the network, so the multi-layer perceptron is composed of 3 layers. Fine. The all bias values are 0. Okay. Now let's see. It has linear 8 times 24, 8. Linear 8 times 16, 16, 4. Okay. Then what is the problem? So since the network has 4 neurons in the final layer, it scans with a stride of 4. It produces 1 4-component output every 4 time instance. Okay, this is fine. You want to implement the above scan using a CNN, right? So what is the network actually doing? Let's see this. This is the network. This is the full connection, right?
Yes.
Okay. These 8 are connected . correct? And
Yes.
then at the next time instant, it has strided forward by 4. So you're going to get 8 over here again, 16 here, and 4 here, right? Is that right?
Yes.
Okay. And so this one is, and this guy is connecting to 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now tell me, how many output channels does the first layer have?
Yeah, this is actually where I have like a difficulty. Like,
Okay, just tell me,
understanding.
how many output channels does the first layer have? Take a guess.
It's either 1 or 8. I think it's 1.
How is it 1?
It's like we have like the kernel size is 8 and the stride is 4.
No, the stride is 4.
Yeah,
No, the
kernel size is 8.
how many neurons do I have here?
8 neurons.
So how many channels do I have?
Also 8.
Exactly. Because each neuron is a filter, is it not?
Okay. Then what's the kernel size if it's not 8?
Okay, so what is the width that the input is scanning to? These neurons are scanning to, are looking at?
24 dimensions.
24?
So 8
How many?
inputs each.
The
8 inputs
width is
each
8. The width is 8, right? Is it not?
Yes.
You have 24 input channels. You have 8 channels over here, and the width is 8. Correct?
Yes.
You can make out from the figure immediately why that is the case. Is it making sense?
Yeah, I think it's making sense.
Professor, one thing, sorry to disturb you, but we have 24 bits into that one
Correct.
of those 8, right?
So that is like saying I'm 20. So this is like saying I have 24 input channels, right?
Yes, but then out of those 24, first of all of them is going inside the at a time is going inside the first first layer of it.
This
That's
layer,
what,
this
that's what,
no, this line represents a connection to the entire vector.
yeah. So all of
So there
them,
are 20.
all of those 24. So the input to the 8 first layer will be 24 into 8. All of them are going inside.
All of them are going inside, but there are 8 columns, right?
Yes.
So the width is 8.
Yes.
These 24 are all at the same time. Correct?
Correct. Yeah.
So what is the width?
Width is 8.
Width is 8. Does that clarify, right?
Yeah.
So Chindan, do I clarify? See on, guys.
Yeah, I think it's all right.
Okay. So this is for the first. Yeah.
So sorry, can I ask one more clarification question?
Yes.
So for the input, so for the in channel, it's always like how many dimensions the vector have.
So here's the thing. So think of this is how you think about it. When you're sliding forward, right? You're sliding forward in time, correct?
Yeah.
At each time position, everything that's in that time position is just at the same time.
Yeah.
The width of the kernel is in time.
Yeah.
Right, which is why the width is 8.
Yeah.
Okay. And these 24 are all the components of the vector at that time.
Okay, so you mean at the same time there are 24 dimensions of data. So the in channel is 23.
Yes.
Oh, okay, I get it. Thank you.
Right. Okay, so Sion, does that make sense?
Yes.
Okay.
Yes.
Now tell me about the second layer. How many input channels does it have?
8. So it'll be
How
the
many output
output
channels? How many output
16.
channels? And what
16.
is the width of the kernel?
1.
Exactly.
Okay,
It's
so
all
let's
about
make
drawing the
sense.
figure, right? Once you draw the figure, it becomes trivial, correct?
So it's like the number of channels is always like the number of neurons, right? I mean,
Exactly.
okay. Okay.
Oh, just questions?
And for the kernel size, it's like how many arrows are pointing at the next level, right?
So the kernel size is the width, how much you're spanning in time.
Okay. So
Right.
basically, from the second, for the second layer, it's like only one at a time of the output of the first layer is fed to the second layer. So the kernel size is 1.
Exactly. One column is going in, right? One set of channels, right?
Okay. Okay.
That's why this bar figure is very convenient, correct?
So in this part, like non-distributed version, there is no sharing of any parameter, right?
There is, I mean, this, if I think of the entire, there is sharing of parameters again. And let's see, but so let's look at the next time. At the next time, I have the same thing, correct? The next time I have the same thing, and then I have these guys, and this one is maybe going to 1, 2, 3, 4, 5, 6, 7, 8. And so then what happens? Finally, if you want to make a decision about is this pattern there, then all of these are likely going through a softmax, correct? Or an MLP, right?
Yeah.
So the big network that's analyzing the entire input is this guy, right?
Yes.
Yeah.
And this column and these subnets are subnets of the big network,
All right.
right?
But,
And these subnets are identical. So these subnets are sharing common parameters.
okay, but when I'm coding up one MLP, the scanning ones, each one do not share any parameter, unlike the distributed, right?
So there is no sharing in this dimension. There is
Yeah.
sharing here, right?
Yeah, so I mean, like, as far as the code is concerned, there is no sharing because the code is coding up one of them, right?
So you'd have to be very careful, yes. But if you're thinking of the individual MLP as this block, as say this block, then I need a different figure. Let me see if I can. I need a different color. So if you're thinking of the individual MLP as this block, within this block, there's no sharing, right?
Right.
But if you think of the complete MLP that's analyzing the entire input, then the individual columns are sharing parameters, right?
Yeah. So actually, at each, how do I say, at each 8 time point, there is no sharing.
So at each time instant, within each time, there is no sharing, yes.
Okay, I see. This is different from the distributed version then, because in the distributed version, there is sharing within each time.
Position, yes.
Yeah. Okay, I see. Thanks.
Right. Any of the rest of you have questions?
Yeah.
Padwo, Chang, yeah.
Hi, Professor.
Gabriel?
So essentially, I used the same logic and came to the same results. But when I'm trying to go through a forward, like actually scanning the entire thing, right? The results are different. I have removed the last ReLU and I inserted a flattened layer. So it's like convolution 1 ReLU, con 2 ReLU, con 3 and a flattened layer. But the results don't seem to match like whatever change I do.
Okay, so I don't know what is, without looking at your code, I can't tell you, but here is what I always suggest, right? And I'm going to say this yet again. Create a toy problem, okay? Create a toy problem where you make maybe, 8 inputs of 2 dimensions, okay?
Right.
And create your little MLP with a kernel size of 2 and an MLP of say only 2 layers or 1 layer, correct? So here you can sort of hand verify. It doesn't even have to be 8 long. It can be just 4 long, right? Just this much. But then here you can hand verify the output and then compare this to what your code is doing.
Got it. Okay.
So that way you'll debug everything. What happens when you directly implement the big problems is that you will invariably have some tiny bug and you cannot distinguish a difference between a bug and a logical error
Right.
because the problem is too complex,
Okay. Got it.
right? So that's why you always start with toy problems.
Hi, Professor. I have a question about the 5.2, which is the distributed MLP scanning.
So the part 2, is it? Okay.
Yeah.
Let me look at the question. Hang on. Let me look at the question.
Okay, sure.
So is everybody comfortable with this answer? First, let me confirm that everybody's comfortable with this answer. Are you guys comfortable with this answer?
Yes.
Yes.
So
Everyone.
one question.
Yeah.
Yes. Can I ask one more about like how the output from the third layer will be fed into the softmax? So actually, at the very last, it would be a flattening layer, right?
Yeah. So this 4 is going to be better drawn this way, right? Make sense?
Yeah. Oh, okay. So it's just like a softmax function applied on the flattened
Yeah.
overall.
Softmax, MLP, whatever else, right?
Okay.
Okay. So what people will often do is they won't flatten it. Very often when you have something of this kind, then this final layer, right? You're going to do a max pool or a mean pool over this final layer across the columns. So you won't flatten it. You will take all of these columns, then do a max or a mean pool. You're going to end up with one vector, and that vector is going to go through a softmax. So this is a standard approach. That is your all convolutional network.
Okay.
Okay. Yeah. Or you can flatten the whole thing, and but when you flatten the whole thing, you're sort of fixing the size of the input, correct? Because the softmax, the number of inputs to the softmax is decided. Whereas if you do a mean pool over here, then it becomes independent of the size of the input. But this is kind of fine detail. Igli, any questions?
Yes, Professor. I had a question about the way the weights would be organized inside the MLP, actually. Because I think my trouble is when reshaping the weights from the MLP to the CNNs. I believe I have tried all different arrangements, but still can't seem to get the correct one to pass the autograde.
So I can't help you with the code side of things, at least not here. But what you're going to get is you're going to get 8 filters with a kernel width of 8.
Yeah, the structure, I believe I have the structure right, because it matches what I have.
So what is happening, what actually happens is this question has been cunningly composed. Observe that there are 2 8s over here, correct?
Huh?
There are 8 filters and the kernel width is 8.
Yes.
It gives you the scope for confusion, right?
Mm-hmm.
So that's probably what's happening.
I think my issue is just the way I'm rearranging the stuff from the MLP.
That's exactly what I'm saying, right? When you rearrange it, instead of giving, say having 8 weights going into the first neuron, you might end up picking, picking 1 weight from each neuron as your first filter. Things can get transposed.
Right.
The 2 sizes are both 8. Had there been a 6 cross 8, you wouldn't make the mistake.
Right. Okay, then
Double
I
check.
guess I'll just try the toy problem solution.
Yeah. Yeah, always try the toy problem and make it asymmetric. You must make your toy problems asymmetric,
Okay.
right? Quadro?
Professor, it seems
Yeah.
to me the second and the third layer stride is one, right?
Yes, yes,
It's
exactly.
a little bit, how do I say, like less intuitive than what the stride means in the distributed version, because in the distributed, I don't know how to say it, like the stride is one is because you're only taking input, like you're taking input from consecutive first layer MLP.
Yeah, but it's just correct. But the way to think about it is this is yeah. I mean, this entire layer of neurons is feeding this entire layer of neurons, right?
Yeah.
So that's so. But this entire layer of neurons is occurring at the same time,
Yeah.
and so this guy is looking at only one time step.
Okay.
So the kernel width is 1, right?
Yeah.
And then this guy is looking at the entire layer of neurons at the next time step.
Mm-hmm.
So over here the stride is 1 bar, 1 bar.
Okay.
Right?
In case if second eight bar how do I say this second 8 bar is getting feed to the first 16 bar, then please correct me if I'm wrong. Then kernel width is 2. Okay.
Correct, but that becomes yes, but that would become a distributed representation.
That would become distributed. But I just wanted to get it clarified that a kernel width and stride how they are exactly working out.
Exactly. So the kernel width is 2, but the stride is still 1, right?
Yeah.
Right? Makes sense?
Yes, right. Makes sense.
Sorry, how do you know the stride will still be 1?
So no, he's speaking of a hypothetical position. Here, question. Right now, here the stride is 1. That's fairly clear, right?
Yeah, I know. No, I mean in the hypothetical situation,
okay, so
16 is kicking into 8 vertical bars, right?
So hang on. So to get to the hypothetical question is actually being addressed in the next problem. 5.2, right? So let's talk about 5.2. Is everybody happy with 5.1? Any questions? Rukayat,
I just wanted to, if you don't mind, I just wanted to know the first layer in a more detailed manner. As in, out of those 8 neurons in the first layer, the first neuron, how many inputs will it be having? Considering we have 24 channels in input.
So every one of these 8 neurons is identically structured, right?
Exactly. Yes, that's true.
And each neuron is looking at 8 bars from the input.
Yes.
Each bar has 24 components.
Yes.
So
but in my assumption, the one neuron at a time can take in only one value, not 24.
Why? Why will a neuron take only one value? What is the point of a neuron that takes only one input?
Okay.
A neuron looks at a collection of inputs, correct?
Yes, but at a time only once. That's what I was
at a time, it's looking at this time, it's looking at this entire collection of inputs. Then it jumps here and then it's looking at this collection of inputs. Then it jumps here and it's looking at this collection of inputs, correct?
Yes, correct.
Did that answer your question? I don't want you kids to go away with any doubts in your head.
As in one neuron will have 24 input, what was it, 24 input in going inside one
Correct.
at that point.
Yes.
Okay.
So here's what happens, right? Again, we're redrawing everything just to be, I'm sorry, I'm erasing this, but I have to, right? So you're scanning. So I have these inputs. Each of these is 8 components, okay?
Yes.
Each of these is 8 components. My first layer has 8 neurons.
Correct.
Okay. The first layer connects to 8 inputs. So each of these neurons connects to 8 inputs. Okay. Or 8 times 24 components, correct?
Yes.
Then you have a stride of 4. And this whole layer strides forward by 4. And then it connects to these 8 inputs.
Yes. That was clear.
Make sense?
Yes, it does.
Okay. Any more questions, kids?
Professor, if it's okay, like, can you just go over once why the stride is 1 in the second layer and the third layer?
Okay, yeah, that's easy, right? This was my so this was my second layer, correct?
Yes.
And this second layer is connecting to the first layer directly like so. This figure making sense, Rituraj?
Yeah, it does.
Okay, wait. Why the question in your voice?
I don't know.
Hang on. This was my MLP. Remember, this was my MLP, right? This
Yeah,
was
yeah.
8-4. Okay, this was my MLP, correct?
Mm-hmm.
Right? 844 or whatever. What was it? 884, 844, 8164, right?
Yes.
8164, 8164. Okay. And then if I go to the next position, if I continue drawing the inputs, then at the next position, I'm going to have slid forward by 4.
Right.
And this would have connected to these 8 guys, correct?
Okay.
Okay, and then this one is these 16 are going to connect to this one, okay?
Mm-hmm.
Right, so now, if you're looking at the second layer, I can erase all of this and you're just focusing on the output of the first layer, right?
Yes.
What is the stride?
Yeah, in this case, oh yeah, it's 1.
And what's the kernel width?
The kernel width is 1.
Yes, right?
Okay. Yeah.
Okay. Anyone else? Quadvo, do you have
Kernel
questions?
width and stride are both of them coinciding each other. Is this a specific case over here, or this will happen all
This
the
is
time?
only for the non-distributed model, right?
Yes, non-distributed model.
Yeah. Once you distribute it, things can be anything. So Quadvo, any questions?
Yes, I'm getting confused about the difference between the kernel width and the layer width. I think the layer width is the number of neurons in the layer, right?
Correct.
Okay, but the kernel width.
Tell me this. How many channels is this layer going to produce?
3.
Wait, how many channels? Why 3? Each neuron is going to produce 1 channel, correct?
Okay, so that makes 8.
Okay. So the layer width is the same as the channel width, number of channels.
Okay.
Right. Kernel width is this guy. This kernel width, right?
All right.
And this is the number of channels, neurons, which is also the number of channels.
Okay, so that's the number of output channels
Yes.
of the layer.
Because
okay.
each neuron is a filter which produces a channel.
All right. All right. All right. Okay, I think I get that.
If any questions?
So in a non-distributed version, only the first layer will ever have a kernel size that's greater than 1.
Exactly.
Okay, I see. Great.
Okay.
But why is that so? What about the second and third layer?
Pardon me?
So he just stated that in the distributed model, only the first channel will have a channel
In the
size.
non-distributed, in the non-distributed model.
Okay. Yeah. So can you explain again why that is so?
Because in the non-distributed model, we are basically taking one single MLP, right? And each of the second layers. So basically, remember what happened. The first layer produced, if I were to draw this more carefully, the first layer was going to produce some outputs, right? And the second layer was using all of these outputs to produce its own outputs.
Yes.
It was looking at only one point in time, correct?
Okay, yeah.
So there's no kernel width.
Oh, okay. All right.
The input layer has the entire job of analyzing the entire input. You're putting a lot of burden on this input layer.
Okay.
Right?
All right. So in this case, where there are 16 neurons in the second layer, connected to 8 neurons. This is a full connection, right? Each neuron is connected to the other.
Yeah.
Okay. All right. Okay.
So there's 16 channels here, right?
Okay. And 4 channels in the final layer.
Absolutely. There you go, right?
Okay.
Just questions?
Output of every MLP over there will have 4 channels, correct?
Wait, no. Output of every MLP? Yeah, here they're going to have 4
MLP
channels. Correct, yeah.
Every 3
Absolutely.
bars. Yeah. So after flat,
if you flatten it, if you flatten it, you're going to get, oh come on, what happened here? Fine. If you have flattened it, you will have 32 bars, correct? And you're going to have 4, so I think you get 128 outputs.
Yes. 1 second. Where did 32 come from?
32 because the stride was 4 here.
All right.
Yeah.
Okay. Yeah.
I mean, maybe plus or minus 1. I'm being careless.
Yeah. After flattening all of them, we'll get 4 into 32 into how many MLPs we have?
So 4 into 32, right? Because you have 4 and you have 32 copies of these guys. That's it.
Yeah, now it's
making sense?
Yeah.
Yeah.
How many time steps were being analyzed, and the kernel width of this was it 8 or 4?
Which one?
The
final
MLP.
layer had 4 channels. The final layer had 4 channels, right?
Yeah.
So 4.
I'm asking, like, how many time steps in total were there? So that there are 8. It's analyzing 8 time steps at a time, right? It's the whole MLP.
You have 128 inputs, but the stride is 4.
Okay. I was 128. All right.
Right. I mean, you'll have to worry about the boundaries, whether you want to pad it with zeros or not. But other than that, it's 128 over 4, correct?
Okay. Yeah. So what was the kernel width for this MLP? I'm trying to remember whether it was 8 or 4. It was 4 in the beginning.
The stride was 4.
Okay, the stride was 4, but the width, as in the number of inputs coming into
the kernel width was 8. The kernel width was 8.
Okay.
Right?
All right. But it's not a rule of thumb that the kernel width always matches the number of neurons, is it, in the first layer?
No, this was done on purpose to confuse you guys.
Oh.
So I want you guys to actually distinguish. Almost every one of you will transpose your weights matrix, right? That's what, and the whole point was to tell you guys to build. We are kind of hoping that you guys will be smart enough to build a toy problem which is asymmetric to sort your code.
Okay.
That's what you must do every single time, right?
All right. Yeah.
Build a really small toy problem where everything is asymmetric, test your code, then throw it on the big one.
Okay. Thanks.
Right? Urval, Yiming, Vinay, questions?
No, it's clear, Professor. Thank you.
Yeah, it's clear.
Damiola, Shanglio. Nothing. Muhammad just came on. He's slightly late to the party. Yeah. All right, guys. Can we move on to the next question?
Yes.
I need at least 6 yeses because otherwise it means someone is missing.
Yes.
All right. Okay. Thank you. So this is clear, right? And hopefully we have sort of resolved this. Wait, I moved this. Well, it's okay. Now let me look at the second problem. The second problem has 8 first layer neurons, right? First layer neurons. Then 16 second and 4 third as before. And then the stride is 4, right? And the figure is given down here. Okay. So let me actually see this. This is where this picture has got to be absolutely clear for you. But if it's not, I was expecting, or I was kind of hoping that you guys will actually redo this with a vertical bar picture. So let me draw this again. 1, 2, 3, 4. And Gladys actually posted the correct picture on Piazza. So Gladys, you may not answer this question because you know the answer, but one of the rest of you, right? So if I want to draw the vertical bar picture, okay, then what is the vertical bar picture going to be like? Anyone want to help
4
me?
bars of 2 in first layer.
4 bars, okay, correct. So first it's going over 8 inputs, correct?
8 inputs, correct.
And then here it's going to have 4 bars of 2 with 1 red and 1 blue. Come on, go away. 1 red and 1 blue. There's no blue, there's got to be a blue. Let me make this. Okay. 1 red and 1 blue, right? And so same thing. What is the stride?
Stride is 2.
Stride is 2, right? So 1 red, 1 blue, 1 red, 1 blue. And 1, 2, 3, 4, 5, 6. 1. Come on. 1 red, 1. So this is your figure, right?
Yeah.
Okay. Then what about the next layer?
The next 2 going to 8. So 2 of these vertical bars going to 8, like a group of 8.
There's 2 vertical bars, but how many? Okay, so there's 1 vertical bar here, and how many does the vertical bar connect to? How many first layer bars does the vertical bar connect to?
2.
Correct. So I have this guy, and then I have this guy, right? And then finally,
both of those connect to one bar.
Both of those
One
connect to
of
one.
One of
Okay.
four.
So right now this is one position, correct? But
right.
there's a stride of 4. Can you help me draw the same network for the next position? For
This
the next
whole thing is
position,
striding by 4. That
so
that's
the
what it
next
means,
the
right?
next position is going to be these 8, correct?
Yes.
And at that position, I'm going to have this guy, this guy, this guy, this guy, and I'm going to have
Okay,
this figure
fine.
here and this figure here, right? And just they're identical, but you can imagine them as being one above the other, right? And this, correct? Is this making sense? Is this making sense to everybody?
Right. So actually, it means when the question says the MLP stride is 4, it means the whole MLP. But the third layer stride is 1, actually.
The third layer stride is actually 1. Yes, beautiful.
Okay. So this point is actually different from the non-distributed, because in the non-distributed version, the stride of the MLP is equal to the stride of the first.
No, so the magic is not in the stride. The magic is in the kernel width. Observe that the kernel width is no longer 1 for the higher layers.
Yeah.
What is the kernel width for this guy?
2.
2, correct? What is the kernel width for this guy?
Also 2.
2.
Also 2. And what is the kernel width for this guy?
2.
2.
Correct? And then how many output channels do you have here?
2.
2. How many output channels do you have here?
8.
8. And how many do you have here?
4.
4.
4? No. This is 4. Yeah. Beautiful, right? So does everybody see how this worked? Igli?
Yes, Professor. My issue is only with the weights.
Yeah, it's just the way you're reading the stuff more than anything. Again,
yeah,
be very careful, right? Because you can make if you just read it transpose, things can break up. Mohammad, is this making sense? Why?
Professor, how would you know that it is distributed in this kind of structure?
This kernel width is more than 1.
I mean, because the first layer you use 2 kernels, and second layer 8.
So it is distributed. It is distributed because at this level I'm looking at a width of 8, correct?
Yeah.
But the width of 8 is distributed as 2 spans of 4. Correct?
Yeah.
Okay, and this span of 4 is further distributed as 2 spans of 2.
I mean, why after you distribute it in 2 fours, and then you just further distribute the fours into 2s?
This is just how I chose to distribute it. So here I'm looking at very narrow patterns, right? Here I'm looking at broader patterns, and here I'm looking at even broader patterns. So I'm building up the broad patterns through smaller and smaller patterns.
Okay, so in the write-up, is it indicated in the picture you attach at the end of part 2 in question 5? I mean, because from the write-up, I didn't notice this is the kind of pattern you want us to have.
Well, it's there in the lecture, right? If you go back and look at the lecture, what we do with distribution, it's explained in great detail.
Oh, okay.
Right? So you have to go back and look at the lecture. I spent a lot of time explaining this, and several of you actually have been through the lecture. Some of you sadly haven't, but several of you have. And the confusion is, it's not an easy concept, but why the distribution is, I think most of you get it from the lecture.
Yeah, I think in fact the homework to P1 write-up contains a distributed example, not the fully connected simple one in the appendix.
So yeah, because we're focusing on the distributed, right?
So Professor, I have a question about like a statement in the 5.2 about the weight. I think like one thing different from 5.1, you said like on the page 12, like you said, after we transpose the weight again into a correct shape, we need to slice the initial weight.
Hang on, Steven, can you come closer to your mic? You're muffled.
Oh, yeah, sorry. So yeah, basically like, can you hear me now?
Okay, I'm not able to make out who was speaking. Chindan, was it? Okay, Chindan, go ahead.
Okay. Yeah. So yeah, basically it's like about in the weight section, there's one extra statement. You said you must slice the initial weight matrix to account for the shared weight. So for that, I'm just confused, like why we need to slice the initial weight matrix, and how is the weight matrix for the shared distributed MLP different from the non-distributed one?
Take a look at the slides.
Okay.
Okay. So this one, let me see if I can pull it up. All of the homeworks and all the quiz questions are trick questions. They're all trick questions in the sense that there is stuff, there are a lot of Easter eggs on the slides. If you don't go over the slides, you're not going to solve the homeworks or the problems. And the half hour you'll spend going over the slides will save you days and days of homework time. So this is just as a warning to you, but let me pull up the slides. Give me a second. This. I want you guys to go to the web and look at lecture 9 slides. Can you do that, please? And in lecture 9, we're going to go over let's see this. Go to slide 47. Can you go to slide 47?
Yeah.
Okay.
Yeah.
This is for a non-distributed MLP. Right? I haven't used the vertical bar representation, but this is for non-distributed MLP. Okay? Is this making sense?
Yes.
Okay, now go to slide 50. This is for a distributed MLP. What does the weights matrix look like? Yes, what does it look like?
Yeah. Couldn't hear you, sir. Couldn't hear you. Your last sentence.
What is this? So what does the weight matrix look like? Slide 50, 51.
Weight matrix. So diagonal of each first layer.
So what is it like? So what kind of diagonal is this? Igli, what kind of weight matrix is this?
The one for distributed?
Yeah, 51, slide 51.
Sort of diagonal, but not really diagonal. If we consider each thing as its own, like a matrix of matrices, then it's diagonal.
It's a block diagonal matrix.
Yeah.
Right, and what are the blocks? Are the
Weights in
blocks
the first layer.
Yes, but are the blocks identical or non-identical?
They are identical. They are identical.
Why are they identical? Look at the
Shared
picture.
parameters.
Because we are sharing.
Because look at the picture to the left. The first 3 neurons are the same as the next 3 neurons, right?
Yes.
Which are the same as the next 3 neurons. Do you see that?
Yeah.
So the first 3 neurons only connect to 2 inputs. Right?
Yes.
So this is going to be a block diagonal where the blocks are all 3 cross 2 and they're identical.
Correct. Yeah.
Right? So if you compare slide 47 to slide 50 or slide 51, right? When you have a non-distributed network, the weights matrix is a full matrix. When you have a distributed network, the weights matrix is a block diagonal matrix. And the moment you compare these two, you also now know why the distributed representation is so much more effective in terms of parameters. Most of the values are 0, right? Yes. Furthermore, the block diagonals are identical. The blocks in the diagonal are identical. Make sense?
Yes.
Chindong, is that making sense?
Yeah.
Yeah.
So I'm wondering, so for the when we convert linear, so basically like for the shared matrix network, it just like have the same size matrix, but because they have the same parameters, so it's spirals. Basically, they have lots
it's going to look like block diagonal. And the kernels are going to be one individual block, right?
Yeah. Okay.
You're going to have to inspect the matrix. You cannot do this with your eyes closed. Look at the data. The homework has many of these little Easter eggs. You're supposed to look at the slides. You're supposed to look at the data, the matrices that you got. If you actually looked at the slides and you looked at your matrix and didn't try to write a program without inspecting the problem, you will spend weeks and weeks without solving it. But if you spend 20 minutes looking at the slides and looking at your matrix, this homework is like a 20-minute problem, literally.
Okay.
So Professor, this definition would then help us in like slicing the matrix for the distributed part, right?
Take a look. I want you to look at the weights matrix.
Okay.
Right? Don't do anything with your eyes closed. Not just in my course, not just in courses. Anytime you're doing anything with data in life, look at the data, right? These are good practices. Any other questions, guys?
Actually, I would say that the stride of the scanning MLP is equal to the effective stride of the last layer, in a way.
Correct.
Okay.
The effective stride, you're absolutely correct.
Yeah, but the actual stride of the last layer will be determined by the effective stride and how the other layers look like.
Exactly. It's going to depend on the architecture.
Okay, great.
Anything else, kids? Any other questions? So I'll wait here for 7 more minutes. If there are no more questions, then I'll hang up. I'll post the video. Remember, when you ask questions, you're helping your classmates. Okay, that seems to have. Do you think you can finish the homework now?
Yes.
Yeah. Almost.
Yeah.
Make sure that you actually construct toy problems. The most time-consuming part of your homework should be the toy problem. Because if you spend an hour building a toy problem, you will save yourself a week of debugging time. Okay?
Yes.
Yes. Thank you, Professor.
All right.
Thank you.
So finally, a lot of you have been asking for time for homework part 2. I can't give you time. Why? Because this homework's, so everybody gets a slack week, correct? During the slack week, you don't get penalized, you just don't get A+ bonuses. And so use your slack week. If at the end of the slack week, we find that everybody is struggling, or 100+ people are struggling, we may give everybody more slack time, okay? But we cannot be, a lot of students have got good marks on the deadline. So those are the only ones who are going to be eligible for the A+ bonus. You have 1 week where you're not going to get penalized. And then you will have 2 more weeks where you can continue to submit this homework with a 10% penalty. We may stretch your slack time if we find enough of you struggling. So in effect, you actually do have time. But what we cannot do is to postpone everything, because if I postpone this by 4 days or a week, I have to postpone the next homework by a week. Then either you get 1 week less for your project or you don't get your grades. Because everything is flush with the end of the semester, right? We don't have time. Makes sense?
Yeah.
Use your Slack, use it wisely. If in a week we find that lots of you are struggling, we'll do something about it. But I don't expect you kids to struggle. Okay? And if you're having trouble with homework 2, part 2, let me know. We'll try to arrange something so you guys can at least get past the hump. This is about you kids learning. Homeworks are not meant to be penalties. They're not meant to be punishments. They are meant to be for instruction. You guys are supposed to learn. If you're not learning, the homework is not doing its job, right? We'll make you learn.
Professor, I wonder when, because I'm actually having trouble in homework 2, part 2, where I don't know how to get 2 image pairs for the verification task, because I thought the image folder structure cannot be used, because instead of the images are in the same big folder, right? It's not separated into different folders with the names of the folder of the class. So so I wonder how actually.
Wait. For your classification task, you do have the images by class, right?
Yeah, I know. Like I'm talking about for the verification task.
So you could be using your classification data to construct your pairs for training, right? If you're doing if you're using something like the triplet loss, then you can be constructing your pairs.
But I'm not using the triplet loss.
If you're just doing classification and directly going from the features that you're using for classification to do your verification, then the training data for the classification should do the job.
But I have to extract 2 images from the verification folder to compute the cosine similarity, right? The
for the verification, yeah, that's what the validation. For the validation and test data, they will be there in that format, right?
No, they are like I don't know exactly how I can extract 2 images from the verification task folder. That's my...
Okay, guys, can any of the rest of you tell her what to do?
Yeah, so for the
sure. Go ahead.
So
there are 2 text files.
Yeah, okay, you can go ahead.
Okay, there are 2 text files in the data. One is verification pairs test and one is verification pairs val. The test pair, that if you open that text file, it has 2 IDs from of the images. Those are the 2 images. We need to check if they are similar or not. And validation text file has the labels with those 2 IDs. They have labels as well as 0 and 1. If they are similar or not, you can use that also if you need. So those are 2 pairs to answer your question.
Yeah, but I have the path, but how exactly I extract the image and turn it into a tensor like I do in the classification task?
Okay, we have to. We can write a new data loader, right? The dataset class, and then put it into data loader.
So actually, we do need to write a custom dataset class, right?
Yeah, I don't think if we have a ready-made dataset class which can consider 2. I don't know. I wrote I wrote a custom one. I don't know about if it's there or not. I don't think so.
I did not write another loader for the images in the verification. You can simply go to the path for both the images. Read the text file that we have in the so we have a validation and a test file, right, in .txt format, and each line has 2 images and a label in case of validation. So you can split each line into a string, pass that string into you can do image.open, put that string inside, so you'll get the image. And then you can just simply do torchvision.transforms.toTensor on that image. So you'll get the tensor format. And make sure you also pass it to the GPU, right? Once you do that for both images, I guess you can get the embedding from your network. And then you can, so you don't need to write the, I mean, you can write a test loader, but that would increase the time. I think you can simply extract it from the paths that are given in the validation and test text files.
Yeah, so the point is image folder cannot be used.
Yeah, because it's not in the format that image folder expects it to be, right?
Okay. Yeah. Thank you.
But the image folder we couldn't use even for testing for classification, right? Because they don't have any labels.
I haven't actually. I'm not at that stage yet.
Okay, so I just inherited that class to use it here, just to add an image in the same class, similar class.
So in case of test for classification, you can write your own custom loader, right? Because it's not in the image folder format. That's why.
Yeah, that's what I was saying. The same custom class, I added one image and I returned 2 images from the same class, and then I proceeded with the verification data loader. That's what I was saying.
Okay.
All right, guys. Thank you. So I think we got most of our issues cleared. If you have any more questions, post on Piazza, post public questions. And guys, the rest of you here, if anybody has questions and you have answers, please post your answers. You will help us a lot by that. Okay. Students learn more from you guys, learn more from each other than you learn from us. This is just a fact. And thanks for being here. If you're running into any problems with the homeworks, timings, whatever, just reach out. Okay.
Thank you, Professor, for holding.
Yeah.
Thank you.
Thank you,
Professor. I was hoping you guys would turn up last week. I didn't think you realized the seriousness of how delayed you were.
I think I wasn't there at this stage, that point of time. I was struggling with homework part 2. Really hope that those basic architectures, baseline architectures, at this time they are really not taking us to B cutoff this time.
Okay, so so if you're having issues, we'll try to set a boot camp or something. Okay.
No, now it's clear. Now I could, but just saying that baseline architecture is
all
not
right,
taking
guys.
us to C.
So if any of you, so this is an open thing for you guys, right? Several of your classmates are struggling. Now, this whole business is about you guys learning, right? If anybody of you wants to hold a boot camp for your classmates, I will support it. If any of you feels enthused to it. Okay. So someone wants to do it, just let me know. You can use this class Zoom or set up a Zoom of your own, announce it. Be careful that you don't, I trust you kids completely. I trust you implicitly. You guys are being very straight. But that said, you don't want to make it so that someone just gets an answer without thinking about it. That's all. Because then the learning purpose is lost, right?
Right.
Yeah. But besides that, if any of you wants to do it in the next couple of days, I'll help you. And I'd in fact appreciate it greatly, because it's going to really get your classmates motivated if you guys yourself are teaching the others. Okay. So if anyone's interested,
I can make slides and everything. But if someone asks any question, I can answer with what struggle I had. And
so I'm not asking you to make slides. Just go on Zoom, pull up whiteboard, right?
Yeah.
Answer questions.
Yeah.
And any of you can just pull in and do it. I can set up an hour or 2 for you guys, right?
Yeah.
Okay. All right. Thank you very much, boys and girls. Thanks a lot.
Thank you, Professor.
Thank you, Professor.
Thank you, Professor.
Bye.
Bye.